Okay, so any questions about last time? So this is the where we are right now. So the topic is linear relations and functions, primarily referring to still familiar business. We just this is the attitude that we have been using, and now it's going to change slightly. So X and Y, remember, you can always remember what the original problem on the first day of classes is the mixture problem. So you have one amount of coffee, the other amount of coffee, and these are the two numbers that are matched against each other without trying to solve the problem, but we're trying to avoid that. And just setting it up correctly, and this is the setup. So every X is measured against Y, so two X and Y emerge independently. Okay, independently to and then they plug in into our equation x plus y is equal to 2, and then if the statement is true, then they're related. We add them to the list. If not, we remove them. Okay, like it's in the bottom. So we're changing the attitude slightly, and that is we are not thinking about two x and y separate, but rather we think of them as together. They're now being paired up. Okay, so that idea of doing x and y, introducing them independently, that is another way to put it, is to say that we have xy as a point on the xy plane, quite literally, but the rest is the same. So you still have x and y, and instead of just plugging them in, we take that xy, separate, and then plug in. And the rest is the same. Once again, statements true or false, and then we plot the point, or once again add to the list, and then plot it probably. Better. So it's the same problem is being solved, but the one at the beginning is crucially different. And then naturally, why so? Because then we could deal with any dimension that we like, as long as we understand what the spaces are. Okay, so then they are made of points on one hand. On the other hand, they are pairs, triples, quadruples of numbers, and they plug into equations. So that may look like now one might have more variables there. And then that's something to be tested. So you need 3 numbers, for example, to plug it into the equation, and then but it's still the same triple. Okay, so as you can see, the work, and that's where we're getting to the current issue, is this is how plotting would be happening. Testing, you have a full field of numbers, and each of them is tested, and then you have a bunch of yeses and a bunch of nos. So every single point has to be tested. I even ignore, I just didn't make a grid. I don't take every single point there. And then you have a lot of no's in comparison to yeses. And then yeses are plotted, no is ignored, and then yeses may be combined together into a line, and then you, okay. So, but the actually yeses, the thing about dimensions, plane is a 2-dimensional, and every point has to be tested. And but the end result is a line, which is 1-dimensional. So the number of the amount of work that you in a way have to carry out is significantly outweighs the output. Okay. So all right. So that is the relation. Our relation is nothing but an equation probably between x and y, and so on x and y you have 2 sets, or in this general case could be. So this definition of the graph of a relation, it applies to any nature set of any nature. But in this particular case, x and y are numbers. xy is a point on the plane, and then x and y are related to y. It is those x's and y's, xy's rather, that satisfy the relation. Then they are the ones that plotted. So this is the set building notation produces that set. Just for the record, what the graph is. It's not a wiggle. Okay, if you ask what a graph is, it might be meaningless. It might be meaningless if you speak of a graph, but it is actually, as you can see carefully, the graph of a relation. Okay, so that's what we speak of. In which case, it's a very specific set lying in the xy plane. Okay. Okay, so all right, so now what do we do about it? About the about it is to begin with, we can plot it as we know, and that's good to know that actually the graph of a linear relation is a straight line, and that's straight line, linear line. Okay, so that's why we call it linear, because the graphs are linear. So that's the general linear relation is ax plus by is equal to c. Any a and b and c are available. It is quite possible that you end up with nothing, by the way. So if the numbers do not come up correctly, so it's still a possibility. So once again, this is the implicit equation of a line. So we're working backwards. Linear on linear relation produces a line, and every line on the plane can be produced as an implicit equation of the line. Okay, so it's the graph of a linear relation. So including the vertical ones. Remember that's what we did last time. So so if, for example, how do we get a vertical line from this? What values of ABC would produce a vertical line? So I skipped over it just a second ago. So what is a vertical? Give me an equation of a vertical line. Any equation of a vertical line. X equals 0. Okay. Okay. So as you can see, x, you cannot throw out x. X must be there for it to be a vertical line, but there should be no y. So when you have both x and y present, that's what creates slopes. Okay, but here you just plug in c equal to 0. So with that example, c is equal to 0, b is equal to 0, and a is equal to 1. Okay, so that's the combination of those three coefficients that will produce a vertical line. On the other hand, if I plug in a0, b1, then we have a horizontal line. And if and then there are some edge cases that I'll ignore for the time being, because now so that's the geometry. If you were to do geometry, that the unlinear geometry, you would represent lines in this manner. Okay, so but really it's not right now what we are concerned with. We are concerned with how do we solve the problem of that say mixture problem. So you have two relations, and you need to find those x and y's. And we know how we did an algebraic solution. It's solving for one of the variables. Okay, solving one of the variables is a solution, and that is, in other words, to interpret it is as if we're creating functions from relations. But first, let's go backwards. Let's go backwards because we're dealing with one relation at a time. So how about we go all the way backwards and actually reduce the complexity of the problem rather than going to the next level, from 2 to 3. Really, what if we're on a level of 2 variables? Okay, so that's we are thinking about going to 3. So for example, coffee made of 3 ingredients. So that's natural. That's what we want to do, and then continue going with climbing the staircase. Okay, but there alternatively we could look at that's what we're going to pursue more than any is actually going down one stairs. One step up, then we go up, and then we start climbing. Okay, so in other words, we want to learn how to actually climb stairs before climbing. So it's easy to climb from 1 to 2. Okay, so if we learn that, then we probably will know how to go from 2 to 3 and 3 to 4 and so on. Okay, so we are moving backwards. That's a step backwards that we want to make. And so what does the linear problem, the mixture problem, is in dimension 1? The answer, there is no mixture. There's nothing to mix. There's only one ingredient. Nonetheless, it is a linear problem, as you can see. So you have a coffee that costs $30 per pound, and we want to get how much do we get for $60? Okay, so that's the setup right here. We introduce XD as the weight of the coffee, and then 3 times X is 60. And so that's the problem. That's so far where we have been with our original coffee with 2 ingredients. But then because it's so simple, we actually have a solution also lined up. So what do? We just solve for X, and that's the answer. So wouldn't that be nice if we could do the similar thing with all dimensions? Is just set up the problem. The setup is already available, but how to solve it, we're not entirely clear how we do it the right way. But it would be nice if we could. Okay, but the point is that there's already one idea that we get from here is that we express one variable in terms of the other, and that gives us the answer. Okay, so similarly, when you have two variables, we want to do pretty much the same thing. Express one variable in terms of the other. So y in terms of x in terms of y. So that's the original problem. This is the graph. It's just an illustration. If we were to solve it, this is a test, so that's not the solution. That's not as good. So if you want to do it, we don't want to solve it by trial and error. Obviously, we know that it is what the meaning behind solving a problem is trial and error. Really, that's what this shows. But we are trying to develop the course is called linear algebra. So we're trying to develop algebra for the situation that cannot be easily solved just the one-dimensional the one-dimensional case. Nonetheless, this is what we do instead of doing it one at a time. Suppose so it's a test but hard. Why is it hard test? Remember what we just discussed is that x and y have to be tested separately. It's a whole a table of values to be tested like this. Okay, true or false, true or false, true or false. So even one single equation to test whether or not a pair x y satisfies an equation, you have to test a bunch of x's, a bunch of y's, linked to each other in independent fashion. Okay, so a bunch of points. So this is the easy way, or at least appears to be. Well, if we solve for y in this case, then how many do we have to test? Much fewer, because each x there will be remember the situation we were in is yes or no question. That's why it was so hard. It was whole square, and then it had few yeses, and then the rest were no's. Okay, so here if we solve for y, so yeses only. Okay, right. So each x will produce a y. Right. So each x will produce a corresponding one. So a little bit of work. This is extra work that we will have to face. We can't avoid entirely. It's a work by hand, and then I'll directly solve the problem y in terms of x, and now every x will produce a y, and then every single one of them will be plotted. Okay, so it's called the system of linear equations. Okay, so just as the one on the left, except now it is explicit. Okay, so this is so this is implicit, and this is explicit. Okay, so then so I'll get to that in a minute. So yeses only. That's the point. That's why we actually want to do it. But the big part of the problem, it might come up shortly on the test, that is actually the part of the class is the ability to set up these systems. Okay, so from the word problems such as these, you have to set up the system of equations. Whether or not you're solving or not is a secondary issue here. Okay, so as you can see here, portfolio instead of coffee. And if you're studying mathematics, you realize there is no difference. Coffee or portfolio or shares, it doesn't matter. It's the same thing. It is mixed together in your portfolio. Microsoft with Apple, and as you can see, portfolio is supposed to worth $1 million, and Microsoft $5 per share, and Apple whatever the piece of the shares $7 per share, and then so that's the first requirement, is that the portfolio must worth $1 million. And then the second one is that you want to be, for whatever reason, you want to have more shares of Microsoft than Apple. So anybody can give me one or two, the first equation for the equation for the problem. Setting up the problem once again without solving it. So we're going to set it up without solving it. So the first sentence in the problem.
Plus 7y equals $1 million.
That's right. So naturally, this first step is really not equation, but rather it is the being very specific, which is not here. Is so I don't want to mislead you here. That's not would be you do not jump like you jump first step number one, introduce x and y very explicitly. So you have to actually say, if you were to write it, let x be the number of shares of Microsoft, let y be the fair number of shares of Apple here. and then you write the equation. So once again, little dictionary, and that dictionary is used to translate the language of words into the language of mathematics, the algebra. So the second one, you need twice as many shares of Microsoft than Apple. So what is it? The number of shares of Microsoft. Anybody can.
Y.
To no, x is equal to 2y, right? I think, right? Twice, yeah, twice the x and y are the number of shares. So as you can see, x is the number of shares of Microsoft, and there are twice as many of them. Am I correct? Yeah. So if you have 10 shares of Apple, then you have 20 shares of Microsoft, which is right. Okay, so let's do another problem. There will be more. So here's a problem of entirely different nature. So we're looking at nutrition. So tomato soup contains 100 calories and 18 grams of carbohydrates, whole bread, it says 70 to 13 carbohydrates. How many servings of each should require to obtain 230 calories and 42 grams of carbohydrates? So same story. It's a mixture once again. It's a mixture, and there are two unknowns, and there are two requirements. Once again, there are two requirements right here. There's a total amount of calories and total amount of carbohydrates produces two equations. Okay, so two ingredients. Okay, the two ingredients of your nutrition is the soup and the bread, and once again they split into two categories of what you pay attention to, calories and carbohydrates. So the data is written in a table naturally, and if there are more ingredients, the table would have been bigger, and the algebraic problem that we end up with would have been bigger in terms of, once again, the number of variables, and as well as the number of restrictions. But they do not have to match, so I don't want to give you that impression. So here we had 2 and 2, just like with the original problem, we had two equations, two unknowns. Here, once again, it's going to be 2 and 2, but that's not going to last forever. You can easily imagine that you have 100 ingredients and then you have only 50 requirements. Okay, so it's possible, and so that's a separate challenge here. Okay, so the table is, once again, you two ingredients, carb, cal, and then, well, actual ingredients would be probably soup and bread, and they are made of the two things about them we pay attention to is carbs and calories. So once again, each of which we know on the meal on the right is that what we want is made of these two parts, and with the two quantities being traced. Okay, so once again, the dictionary: X number of serving of soup, Y number of serving of bread, and then we started rewriting those sentences inside the parentheses, so inside the quotation marks, into algebraic equations. Okay, so X servings of soup plus Y servings of bread is together gives you the meal, and then that applies to both of the things that to pay attention to, the carbs and calories. So X times 100 plus Y times 70. We're just pretty much reading nothing but we're reading the first row here, but now with just a list of data. Here it is now translated into a relation between the data with the introduction of X, a number of servings of the soup. Okay, so and then for the so that's how many calories you've got, to 30 kilocalories technically, and the for the second row as kilocalorie. Carbs is X times 100 plus Y times 70 to 30, and for calories is these the numbers. Okay, so right away we have the two equations. If they're conveniently units are different. So if you watch for the units, you will never mix these two problems together, two variables together, because you will never add carbs to calories. So just like pounds and miles, you don't add them together. So and that's the extra work. But on the other hand, that's make sure that there is no, there is no mistake there. So it's an extra clue for you to avoid mistakes. If you're not totally understand the problem, that will help. Okay, so that's the system of equations. Doesn't look that the numbers are bigger, but otherwise it's the same problem as before. So how are we solving it? We know roughly how. We solve for y, plug it into x. If we were too forced to do it, but that's not really not effective. So I'm sure, by the way, there are apps doing exactly that. So you plug in your current meal maybe in the you breakdown in terms of the amount of calories and carbs, but on it on either that so direct that's direct computation. So direct computation is so direct. Direct meaning that from amounts. So in this case, the amounts of how much of the soup and how much of the bread you got, and the two amounts again, amounts of the direct computations. Okay, so in other words, so because you know how much of which, and if you decide x and y are given, if x and y are given, then you can find the right hand side the amounts of carbs and calories in the output in your meal. Okay, so that's direct computation, but that's not what we're doing. So that's a no. We're doing the opposite, indirect. So this is what we're doing is outputs are known. It is the problem as I just tell you that app that you might have. You plug in the amounts of ingredients into your app, and then it tells you how much it is worth in terms of your meal is worth in terms of these two, in terms of calories and carbohydrates. But alternatively, you can go backwards and you can actually tell this is how much I want to have carbs and how much I've got carbohydrates. Okay, and it tells you how much of the soup and the bread you should have. The opposite problem. Okay, rather the direct and well, actually the word is inverse. So the direct problem, which is easy, okay, plug in and compute. That's it. Or the inverse, it's hard. Just like with plugging in values, computing is easy. Solving equations is hard. Okay, so all right, single function. So and then another type of problems is so the problem of mixtures is split into two parts: setting it up and then solving it. So the harder part is naturally to set it up, and the simpler one is when the system of equations already have there, you solve it. Okay, so as you can see, you just to practice, you can just try to solve these equations. Okay, so okay, so a few examples. Okay, so this is the relations relations having the same graph. Okay, so x plus y is equal to 2. You are allowed to do algebra with it, so you can move stuff around, multiply, divide, and all of these represent the same relation. Okay, the same relation. So meaning what makes two relations the same? What makes two relations the same? Well, this one is it. So same. What does same mean? It's the answer should be the same as if we were talking about one single equation. So, for example, x squared is equal to 1 equation, and you have x squared minus 1 is equal to 0. So it's also same. In what sense it's the same? Ignoring the algebra. So that's a hint for you to answer the question. What makes these two equations the same is not algebra. What makes these two equations the same? They look different. And you can, if you allow yourself to do complicated algebra, you might end up with something unrecognizable problem, unrecognizable equation. So would I know, how would I understand where these words, the two equations are the same? What is the same if they look different? What remains the same? We talked a bit about that. Let me give you a hint. It is the end result is the same. Hypothetically, if you have solved the problem, the equation, the first one or the second, the end result is the same. Okay. Remember what language we use here? Solving an equation means producing what? What? An output. Well, no, not an output, but it's an output, but not in the sense of a function. Right now, we don't speak of functions here. So, yeah. So, what does it mean to solve an equation? What?
Solution.
So the solution, and to these, not a solution, the solution, and to make that point more precise, the solution set. Okay, so solve the equations to produce the solution set, which consists of all possible solutions to the equation, which is not, even in this case, it's not one single number. So producing the solution set is solving an equation. So then the two equations are the same in that sense if they have the same solution set. Okay, so that naturally is plus or minus one. Both of them have the same solution set, and that's why you can replace one with the other. It would make no difference. Okay, similarly here, more complicated because instead of having a 1, 2, or whatever number of numbers, here we speak of pairs, and so but the plot still applies. So it's a solution set. The solution set is still what we want to end up with. And instead of having, once again, this is plus or minus one, two numbers, these are lines. So the solution set is a line, and all of these have the same solution set. It is the line, which does look like this, but more looks like this. Okay, they have exactly the same solution set. Okay, so that's what it means for two relations to be the same. They have the same solution set, and the solution set is really what we're at. Okay, so solution set is a line because these are linear relations, and then and all of these, if you do this algebra, as long as you don't do something something crazy, it will produce the same solution set. Okay, with your algebra. So then, what is the point? The point is, so this is solution set, and there are exceptionally important solution set. Relations are at the corner here in the red and green. Okay, so you can see what makes them important. And they're not important, they're special, they're functions because they are now explicit. So y in terms of x or y in terms x in terms of y, it doesn't matter. If you have two, you have two. You have one, then you have one. But there are two expressing one in terms of the other. That is the tool for solving these equations for the time being. Probably the easiest way to solve these equations is to solve for one of the variables, producing a function, and then plug it into the other. But if you have only one relation, then these are just still relations, the same relation, but they are now explicit. Okay, so to compare is graphing. Once again, what the point I was starting to make is what it takes to plot the graph of a relation, generally speaking, the one in the box, or what it takes to plot the graph of a function, which is say the red one. Okay, each x produces y. That's the thing. So this is once again how we plot the graph of a relation. Every xy is tested, and then yes or no. Okay, true, false, and then we plot or do not plot. What do we do with the function? Each x will produce a y. Each x will produce a y, and so then xy is plotted. As you can see, there are no numbers, so it's always a yes. Every x will produce a y, and that will produce a point. So you do not go like this through the square. Picture here. Somewhere. Hold on a second. Yeah, so in the picture you saw, remember going through a square of points like this, and then you have a bunch of yeses and nos. But this one does not require you. Instead of going through like this in this manner, like this, you're only going like this through the axes, and each one produces y, and you plot it. So you of course you're familiar with function, you're familiar with how they're plotted. That's how. So, okay, so let's solve once and for all a linear relation. Okay, so there are, as you have seen already, there are several possibilities depending on the choice of A, B, and C, and that comes up whenever you try to solve for X or for Y. Okay, so if there is no Y, you cannot solve for Y. If there is no X, there is no. So these are A and B are equal to 0, and do not allow you to solve the problem for that variable. On the other hand, you don't want to divide by 0. So that's another issue. So if you have ax plus by and you want to produce a function of y, then you're supposed to divide by y, and so but by b, so b cannot be equal to 0. So that's case number one, is when b is not equal to 0, we simply divide by b, and y is expressed in terms of what's left. Okay, so that's the solution. A at the bottom, negative b, negative a over b, x plus c over b. So as you can see, negative a over b is the slope, and c over b is the y-intercept. There you go. If a is not equal to 0, we can divide by a and pull everything to one side, and we solve it with respect to x. Same equation. There are two different cases. It's the same relation, but different representation, and then we have a function, and that solves the problem. Like I said, it is the point of solving it is for the time being is to know what the moving backwards to familiar territory. And so linear functions are familiar. So once again, negative a over b is the slope, and this is the y-intercept. And here we have instead, this is the slope, but the other slope. Let's be clear that there is a x with respect to, so this is x-intercept. The slope is x over y or y over x. So it's they are opposite. Depending on which of the two variables you choose to be the independent or dependent variable, the naturally the whole picture flips, and therefore the slopes flips too. Okay, so we'll deal with that when necessary. Okay, so every linear relation then with these caveats, and these are the caveats when it is or is not possible, can be when one or the other is not equal to 0, then a linear relation produces a linear function. Okay, so that's the illustration here. If you take all the linear relations, some of them are you can solve case number one, which is case number one and case number two. Okay, so and they do not fully separate, right? It's possible to have neither a nor b equal to 0, in which case we have a slope. Okay, literally, by the way, the intersection of the two cases, 1 and 2, is when both a and b are not equal to 0, in which case you have a sloped curve. Okay, otherwise, if one of them is equal to 0, then you either end up with horizontal line or vertical line. Okay, that's what lies outside of this kind of a generic situation in pink, when we have a sloped curve, and then which means that both 1 and 2 are satisfied, and we can think of it as a function of y depends on x, or x depends on y. Either way. So that's okay. I'll skip that. Some exercises, solving equations. One, y and x always produces confusion. What to do with this when either y or x is missing? That's the keep the attitude of this theory. We were really relations is what we're getting. You remember the equations restricting certain mixtures are actually relations, not functions. And so that's what whether or not you can actually solve for it for one variable or the other is a second issue. And then which one is even later. If you can solve for x, you solve for x. If you solve for y, you solve for y. So so when you run into a relation like this to x is equal to 3, you cannot solve it for y because there is no y. But you can solve for x. So x is equal to 3/2 is your answer, and then probably you have to be say what you see. So x equal to 3/2 is as its graph is what? X equal 3/2 is a vertical line, right? So similarly here, this will produce a horizontal line. Okay, so we are not at all concerned by the fact that maybe y is missing. It's just remember these restrictions. So imagine that if you had more restriction than these, whether it is ingredients of some kind or not. So maybe you have there's when you are maybe one of the parts of your meal has no carbs in it to begin with. It's you cannot predict that, no, you can't expect that to present everywhere. It literally would be like 100x plus 0y is equal to, I don't know, 70, whatever. Okay, so it's possible that certain ingredients will not appear so in a particular combination. So we do not know ahead of time, and so we want to include that possibility into our theory. Okay, so once again, to make that point one more time, function to, if you are dealing with a relation, this is the amount of data you deal with, and every one of these a combination of x, y produce a number in the table, and that number is then seen whether or not satisfy the relation or not. Or everything is expressed in terms of y in terms of x, and then all we have to do is just to go through lists. That's the difference. An array of numbers or it's a list. So that's the difference. So the array of 7 by 7 or list of 7. Okay, so 49 versus 7, and the only thing that we need to do to achieve this improvement is solve for y. Okay, so but it is think about, so naturally all these testing would be done by a computer. So but the solving the equation probably would have to be done by hand and by yourself. So once again, plotting yeses and nos of a relation, plotting a function, it is only yeses, and so you just plot one point at a time. So, so the issues, of course, it seems like the work is if it is done by a computer, what's the difference, right? What's on the left and what's on the right? Naturally, you do way more work on the left than on the right. But is there anything else? Is there anything else that might come up if we ignore the computational price that we pay? If we stick to the relation. I guess it's kind of subtle, but you might end up with nothing but no. Okay, you see how? Well, ask yourself, why would you get a yes in the first place? How would you know where to look? Right, knows what I'm talking about? So we were lucky that our grid that we chose matched the curve, the line. Okay, and so that's why we got on the left, we got a bunch of yeses. But hypothetically, all we have is this line, okay, and then we're testing it in what manner? Well, either by grid. It is actually quite possible to miss it. Or does your grid that you chose to as a testing, why would it hit that line in the first place? Okay, it's so thin that it's so easy to miss. So, for example, if I choose this as this grid is chosen to be a negative only 1 by 1 squares. Okay, so these are all ones, 1, 2, 3, 4. Think of a line that, can you think of a line that will not be touched by this grid, not the grid, but rather the testing points are these. They are marked here with yes and no. You can easily think of a line that you will miss altogether. Can you? The line that does not contain any of these points. Well, a horizontal line, by the way, would. An easy answer is actually horizontal line. I was thinking about something more complicated, but this line will not so y equal 1/2. Y equal 1/2 is a total miss. So you're trying to understand a line, okay, by testing points, whether or not they satisfy your relation or not. And then if you find nothing, and then you create a grid, and then you create another grid, you dense a grid and dense a grid, and then you keep missing the line. It's not that complicated. It seems like it's pretty hard to actually navigate between those points, but it's not. So one is a horizontal line, like I said, but there can you think of an incline that will never hit any of the integer points. So y, think about y equals, say, mx. Let's say mx. Let's forget about. Let's suppose 0 is let's accept 0. So this will pass for 0. So what m should be to miss everything else? Is the problem clear what I'm talking about?
In the given function that's plotted, we want to miss that completely. So we use like a -1 for m.
M negative 1. No, m negative 1 will go through. No, it will go through the. This is -1. It will go through diagonals and hit these points. The idea is x is an integer, so the question is actually how do we miss those points? The answer is if x is an integer, what will make y never an integer? To miss all the points except for 0. Let's accept 0 as if it's there. So we have y, we have an equation of a line passing through the origin, and then we try to miss all of these points. And just to make an example, to make the point that it is possible to miss everything, and using the grid is not solve the problem, even if we have all the computing power in the world. So so then the question becomes, if x is integer, what value of m, one single value of m, will guarantee that there are no other y's other than 0? So integer times m, not integer ever. Exact. When the integer is 0, then of course you will get 0 at the end. So that let's accept that. But otherwise, no zeros ever. So can you think of an example?
Would it just be any decimal value?
No. If you take 1/10, you take 1/10, you will end up with if you plug in 10, x is equal to 10, you will get 1. It's an integer. So
We're trying to miss both the no and the yes plots.
no, I would have only nodes. What choice of m, this which is the slope, allows to navigate between those points safely. Other decimal, what? An irrational number. An irrational, that's the whole point of a rational number. So if m is any fraction, doesn't matter what that fraction is, eventually if you cancel the denominator, you'll have the integer, right? So if this is p over q, right? If m is equal to p over q, then I multiply by q and I end up with p, right? So and I hit one of those dots. But if it's irrational, right? If it's irrational, it never is a fraction, and it doesn't matter what you multiply by, you will never hit the integer point exactly. Okay, so the point is that it is possible, and if you try to make the grid denser, there will still be a ways to get around it. Okay, so once again, the irrational slope will do the trick. So m is equal to square root of 2 is the way to demonstrate that it can happen. So with all computational power in the world, you can still try to plot the relation might produce literally nothing. Okay, so that step might be of producing a function. It can never happen, right? So if you have made that step and you have produced a function, then you will never miss a point. So every point, every x you plug in will give you y, and you will have all the points there. So So whatever it's worth, it is then it pays to do this little algebra. So I guess the reason is just the pure data will not necessarily be, you can handle it even with the no restrictions whatsoever on your computer, on computing power. You still will not be able to solve the problem. Naturally, if you make denser and denser the denser and denser grid, at some point they will be so close to each other that they will be, your accuracy of your computation will probably come into play, and then you'll say, well, these 2 points are actually the same. But that doesn't sound like a good plan. But this is so. Solving for one of the variables is a good plan, even though it is hard to execute with a computer without kind of a more precise plan. So you basically will have to execute division somehow. Anyway, so that's this topic. Functions are represented. So let's talk more about functions and so relations is a starting point because those are restrictions. Whether or not we solve them somehow, that and produce a function, that's how so far is set aside. And now let's see what is that we expect to happen at the end when we solve a relation for one of the variables. What is a function? Function is a blank box. Okay, so you should appreciate it in a kind of a computing spirit. That something is computed there, you don't know what and how, but you don't care. Literally, it is about producing outputs for each input. That's what a function is. And any day or day of the week, it should produce the same output. That's what makes a function. A function is that there can be only one output if the input is specified. So the nature once again is, even if we stick to numerical functions only, then the nature of how it's computed, it could be variable. Is there a formula there? Maybe not. Maybe several. Maybe some in a row. Maybe it is like there's a formula. Is there or is there not a formula how to produce your tax bill from your income? Maybe there is, maybe not. But usually just if you ever seen the brochure of how to fill your taxes. Your taxes. It is never one formula. It is a step by step. Subtract that and that, multiply and so on, and then there is no single formula, but it could be a sequence of steps. Cosine. Suppose you don't even know what cosine is. Doesn't matter. You know, if you are told that it is a function, then you can use it. It's told with a function, you know what it's supposed to produce, cosine, and then you can use it as a function. And so you can be part of a bigger computation. It can be solve a problem that you're not familiar with. It's the blood box. So it's a box with a COS on it, and you can. So that's the point. It is a function. So as long as you know how to what's for, you can use it, even though you have no idea how exactly it's computed. Including a good example actually is a calculator, right? So how do they compute all of those functions? You don't know, but you use that calculator really heavily, right? So it's the same exact story here. So a flow chart. This is a very important place because we speak of sequences of steps, sequence of instructions, sequence of functions. Okay, so frequently not enough attention paid in pre-calculus or even calculus to make this a well understood concept. So a sequence of steps, sequence of instructions, sequence of computations. What's the word in mathematics we use for it? Well, I do hope that the flow chart is quite clear what's happening here. Have an input number, then you add 3, you multiply by 2, you square it, and that's the output. Okay, 3-step procedure. So it's a big deal. Happens all the time in mathematics. Usually, there are formulas for each of them. So this is how you would do it. Even though it's already unambiguous and the computation is perfectly straightforward, you can assign each variable here to a name of variables if you were to write them algebraically. That all of these is good, but it's not necessary to understand what's going on. And I just wonder if you recognize this from the past in mathematics. What do we call it? Well, yes, but even more basic. So it is an algorithm, flowchart, sequence of steps, Okay. Oh, if you, each of these boxes is a function. Okay. Yes. What's the word? One function, another function, execute them consecutively. What do we call it? Consecutive computation of functions. Like this. So for example, x plus 3, one function, the next one is y times 2. What do we call it? We combine functions. We can combine functions in a number of ways. We can add, subtract, multiply, divide, and there is the fifth operation. To combine. Nobody remembers the word. Starts with a C, but not combination. What? Well, no. Well, we'll come back to your.
Is that what you said?
Starts with a C, yes.
Oh, a C.
Combination. Potentially using the incorrect word.
What are we talking about?
The first three letters are the same as in the word combination. No. Well, you correctly, if you were guessing the word, the next is P. What? Close, composite, right? Composition. That's the word. Now you remember? Calculus 1, chain rule, all of that. So, and that's what it's about. It is indeed about algorithm. It's about a sequence of computations. So you don't really need all of these words to understand what that is, and you have a multi-step program that you have written, and naturally you don't really need a one single formula. You consecutive. There is nothing wrong with computing one step at a time. But if you were to understand linked back to mathematics, then you express, as you can see here, you name the variables, then you write the formulas for each of the functions. So if x is the variable, then the function is x plus 3, that gives you y, which plugged into the next box, which is y times 2, which is the name of that variable that comes out is z, and then the next operation is z squared, and that produces the last variable u. So three functions, and then the language in mathematics is used here is the composition of these functions. In other words, it's substitution, right? So if you were to produce one single formula, which once again, do we even want to? And then you would substitute, right? You would substitute literally what's happening here, that y is equal to x plus 3, you would substitute into y equal to 2, giving you what? Z in terms of x is what? Z in terms of x. Replace y with x plus 3. That's substitution. Okay. So, but once again, only if you want a single formula, which you might never have. Okay, so function, input, output in the middle. That's just a way to chart with the black box, which could be made of many functions inside of it. And so name of the output, input variable, name of the function, and then the interpretations are multiple. So list of instructions, what we just saw is all called an algorithm. The algebraic formula, when you substitute, you have one single formula, which may be cumbersome, but maybe, there's a point there to substitute. Maybe there will be cancellation or something. You might see something something insightful into a simplified formula. Okay, list of pairs and outputs. That's what we started with. So this is now. This is general. Outside of the source. That's what four functions are. This is what we started with. So that's been a while. when we started with the function is nothing but a pairs of inputs and outputs. And then the graph, okay, so that's we did that too. And then a transformation that comes up much less commonly, but it is very, very important. A transformation of what? Of a number line. Number line, it transformed into another number line. So we'll get to that later. Let's review these. So we already looked at the algorithm flow chart. Okay, algebraic representation. This is f of x is equal to 3x minus 1. Okay. Once again, familiar notation, worthwhile taking out a look at it. What stands for where independent variable inside the parentheses, outside after equal sign, you have the dependent variable, literally depends on x. The function f is outside the parentheses. It's nothing but a name. It could be a one letter f, or it could be COS or SIN. Name of the function might be more complicated. And these are the same function. As you can see, also there's a point because the formula is the same, even though the names of the variables have been changed. So is it the same function or not? That depends on your point of view, but certainly compute the exact same values. Okay, so that's the substitution. You can think of it as a funnel if you like. You can literally plug in these values. There's a square, and you put a number there, and then as if it is, like on a web form, sometimes you write your name, and then your name, populates the rest of the windows in that page. So that's insert input. Wherever you want to insert input, same input. Okay, so insert same input, or it automatically whatever you plug in on the left also plugged in on the right. So now naturally algebraically we replace it with we have an x there. Okay, but technically it doesn't matter. The name, you don't really necessarily need a name for the variable in order to be able to execute it. Well, once again, it's just write in the same number in all the squares, and then you have your substitution. But that's we are not done, because now we can substitute functions too. That's the composition, right? So the input could be a number, but could be another function which creates two consecutive computations. So here negative t plus 5 is the input, which means that you start with t, then compute negative t plus 5, and then you get to f. Okay, so that's a two-step procedure. Whether we substitute or not is it's a placeholder. That's what x is. You can have a square, literally a placeholder where we type things in, or you have an x to just, x or everywhere, and that x is the same number. It has to be replaced with the same number in order for the function to work. Okay, so once again, sequence of steps. We already seen it, so just keep plugging in. Okay, I'll skip it. Decomposition. So once you understand composition and substitution, you should be able to go decomposition and go backwards. So somewhat complicated formula, you should be able to split it into consecutive steps. Okay, so that's how we deal with formulas really, because if a formula is any complicated to any degree, then you don't compute it once unless you type it entirely into your computer. So you actually execute it with squared, then subtract 3, take square root, add 5, and then produce output. That's how you would compute it. So you look at the formula, ask yourself, do I know how to compute it by hand? And if you do, then that would be not very easy to decompose it into steps. And then no matter what x is, if you know the order of operations. So then naturally, the order of operations matter. But usually the ambiguity of the order of operation, that issue that may be discussed to death, just the parentheses are your friend, and just look at where the parentheses are, and so you know which operation comes first. So this is very unambiguous. You have to square it first before you get to subtraction. So in other words, you do it inside out. Okay, inside out from x, and then inside out until you get to the y. So that's a scale also that you should bring from pretty much pre-calculus, the composing functions and decomposing functions. So this is if I take this like this. If I take this function, described as a sequence of steps, I should be able to produce a single formula or substitution. Or if I have a single formula, I have to be able to split it into steps. Okay, so that's the scale of that we use a lot in mathematics. Okay, so one I mentioned also in your presentation of functions is a sequence of a sequence of pairs of inputs and outputs, such as this. Okay, so naturally, the point of it is it's a numerical. Naturally, it is you cannot have infinitely many of them, but you can produce more and more and more, getting better and better idea of what the function looks like. Especially if the formula you plug in it only once, and then you just add more numbers if it is a spreadsheet. So I could do it here at one unit at a time, or 0.3 at a time, or whatever I choose, and denser selection of sampling points. So this is sampling, and you can choose inputs close to each other, and I'll have more and more data. Okay, so as long as the formula is present, this is my function right here, and then I just plug in more and more values. The formula has to be typed only once, and the computer does all the hard work for you. Okay, so that's once again another representation. And then the graph, which we just talked about, the graph of a function of one variable, that's what it is. All pairs of x and y. You do it by hand just to demonstrate that you know how to do it, but like this, one at a time, each 0, 1 plotted the orange dot, then 1, 3 is plotted the green dot, and so on. But ultimately, it is plotted for you by a computer if you plug it in. If you have even 5 points, makes sense to type them into your Excel and then push, highlight, push, insert chart, and then you have your chart. And then once you do it, the red one. Okay, the red one is the data. On the right is Excel. You might ask Excel to fill in the blanks, and then it does. And so it creates that curve, which is a guess, but quite productive. Okay. All right. So the transformation, we'll get to that later. The algorithm is once again a multi-step procedure. And as long as there is no ambiguity about how to get from A to B, then you have your function ready. This once again formula, multi-step procedure. I'll let you read it. This is the idea of how to visualize a function without. Remember this one without the graph. You domain and codomain are aligned like this rather than being perpendicular. Then the arrows show where each x goes. Okay, so then you can think of this as a transformation. Because you can see how you can see what happens to the what do the arrows tell you about what is being done to the x-axis. Can you see what's happening to the x-axis? The arrows kind of pointing away from each other. What does it tell you? So if you were to think of the x-axis as about a rubber band, what's happening to the rubber band here? It's being stretched out, right? So the arrows pointing away from each other means that the 2 points that were this close to each other, then after the stretch, after the transformation, they are farther away from each other. So that's a way to how to interpret functions. In that different way, which deserve a lot of attention because we are going to high dimensions. Okay, high dimensions, and then the graphs are out of reach. Graphs, a great way to visualize functions, but we cannot beyond dimension 2 or 3. We cannot visualize them anymore. So, but transformations are more is still quite good benefit. Okay, so counterpart. Okay, so this is, remember that the requirement for such those bunch of arrows. The only thing that is required is you cannot have two arrows originating from the same location. You're also not allowed to have like this on the right, too many values or too few values on the case one, item 1, when x over there at the top has no counterpart. So these are not functions. Okay, so that's. So how do you deal with it if you were in the computation of, so you have a formula and you have division by 0, and so that you cannot plug in x equals 0. What do you do? The answer is that is actually you have to redefine the domain, right? So in order to have the function still working for everything, and so in other words, function is not a formula. But rather formula, if it is a formula, then it's not just a formula because you have to supply the specified and everything. Okay, otherwise, you see what the problem might be. You have a formula and there's an exception situation there. Okay, but you think about it, but it is a black box. Okay, so maybe you pass it over to somebody else and say this was confused, and they start using it, but then they're unaware of that exceptional situation there, and then there is a breakdown. Okay, if you plug in that 0, you don't know. So that's why that black box actually has to come with a written warning on it. These are the allowed values. These are the possible outputs, inputs rather. But outputs also something to worry about. So there's only one for each x. Okay, so if the domain is specified, so that's the assumption. And so let's see what can be violated with these representations. So once again, if you have arrows, you have too few or too many arrows. Okay. So if we were to write formulas, that's to watch out for plus or minus. That's not a function because you right away have two outputs. Okay. In numerical representation, as you can see, same story, but it might be hidden in the data. So the same input produces two different outputs. You have to actually search and to make sure that it does not repeat itself. So in algorithm, well, if there is an unambiguous step in the middle of your long algorithm, that's not a function anymore. Okay, so if you plug in date, it means that tomorrow the output will be different from today. Okay, graphical representation. Here it is, two values. X's are on the horizontal axis, and that A has actually two outputs, kind of in a subtle way, but it is two outputs, so it's not a function. So then to solve the problem, you'd have probably something like this. Okay. What else? Transformation is literally pulling thing apart. If you want a transformation, that's not a function. So it's actually harder to imagine. Okay, so linear functions. So linear functions means that it's made of two operations, and that is addition, subtraction, and multiplication. Okay, so you don't even need to think of it in terms of subtraction. It's just, you remember, subtraction is just adding a negative number. So it's literally about adding and multiplying. And so then you can combine as many steps like this as you like, and it will always be continues to be a linear function. That's what we're studying. So all of a sudden, speaking of functions in all of these contexts, a variety of functions you can think of, but we're studying linear algebra, and that's the humongous simplification that we are now making, is that all functions will be linear, period. Okay, so like I said, that is the simplification. That's our limit our attention to a function that are all linear. And if it seems too simple, then it is. But then you remember where complexity comes from, dimensions. Okay, so when dimensions go up, these problems cease to be simple. Okay. Constant function, the simple linear function is constant. Then simplest linear function that's not constant is x. Okay, so which means that you do not do anything to the input, you just pass it, and that's the output. Okay, so that's the simplest function. And then you can combine this is the data, this is the graph. So once again, the most simple functions. The main characteristic of a general linear function is its slope, rise over run. Okay, so familiar with that, I hope. So it is literally can be computed. The run is the change, horizontal change over or rather the other way around. So the vertical change over the horizontal change, you can go from A to B. You can go from B to A. The result is the same. So that does matter. And because it is a straight line, it doesn't matter which points you pick. I can pick these 2 points. I could pick those 2 points, and it still works out exactly the same way, because the difference between curved curve and straight line is that the slope is the same everywhere. Okay, I'll stop here. Next.